Hello everyone. In this lecture, we are going to introduce certain famous algorithms for trees. So first, record the following general algorithm to grow a tree. So let G be a graph of order n, and U be a vertex. So we set up a vertex subset U consisting of a single point small u, at the very beginning, and F to be an empty set. And while there is a vertex X in U and a vertex Y not in U, such that the edge incident with them is in E, then we do the following two steps. First, put Y in U, then put alpha in F, and then we can repeat second step until there's no such X, Y, and alpha, and then put U to be T to be the final result. Okay, then conclusion. If G is connected, then we want to say T is a spanning tree. Okay, and it's not conclusion, goal. Okay, then the question is how to make more specific choice of Y such that the above goal is satisfied. And the following theorem says the above goal is always satisfied according to this algorithm. Let G be a graph, then G is connected if and only if T constructed as above is a spanning tree of G. Prove. So if T is a spanning tree, then it's easy to see G is connected. On the other hand, if G is connected, then from the algorithm we know that T is connected, and okay, let's suppose G is connected. noted that by the algorithm, T is connected and F, the kinetic of F is kinetic of U minus 1. Therefore, T is a tree. If U is a vertex set of T is different from V, then there's a vertex X in U and a vertex Y not in U, such that alpha is in E. Alpha is an edge incident with X and Y. So this is by connectivity. Connectivity of G. Then this is a contradiction, because if we have such X, Y, and alpha, then by the algorithm we should add Y to E, Y to U, and alpha to F. So the above T is not the final result from the algorithm. Okay, then we are done. Okay, so the remark is, in general, the above algorithm suffices to grow a spanning tree. But an immediate question is, what if we expect more for the spanning tree? From the previous lectures, we know that usually for a connected graph, there are many spanning trees. Okay, so some are very special, satisfy certain properties, some satisfy the other properties. So how to make a more explicit algorithm to derive certain spanning trees with specific properties. So here first we introduce the following, which is very famous. Breadth first spanning tree, BFS tree. And from, so we can use the graph to illustrate a little bit. So U is a prescribed vertex. Okay, then we first draw. So when you construct trees, we include first those with distance 1, distance U1, and later on we will call this dx. Okay, you include all the nearest vertex, and then you include those vertex with distance 2 from U. And then distance 3. Of course, it can be empty. So from this, this is how we do the breadth breadth first spanning tree. And in the following, we will associate each vertex with certain invariant. So each vertex X associated with two numbers. So first is breadth first number BFX. So this is the order in which vertices are put into the BFS tree. And second, so this is used to describe the history of the vertex in the growing process for the spanning tree. And second is dx, which is distance of x to u in BFS tree. Okay, here you may have some confusion, ambiguity on this. We will illustrate this by the theorem in the following. Okay, and for BFS method, dx is more important than the BFX. Okay, so I first describe the algorithm. So BF algorithm to grow a BFS tree rooted at U. So let G be a graph such that it's of order n. Let U be a vertex. So we fix U. And first step, put I equals 1. So this is a counter. And U is a vertex set. DU is 0. BFU is 1. F is empty. And T is UF. This is setup, initial data. And then if there is no edge in G that joins a vertex X in U to a vertex Y not in U, then stop. Otherwise, determine an edge alpha incident with X and Y such that X is in U, Y not in U. And X has the smallest breadth first number BFX. Do the following. So here you have three properties. So if there's an edge with one vertex in U, one vertex not in U, then you need to choose. So this is first requirement, one in U, one not in U. And then second requirement is the vertex in X should be the smallest in the sense of the breadth first number. So we just set up the breadth first number for y as I plus 1 because it follows x. And secondly, put dy equals dx plus 1. Thirdly, put y into u. We are increasing the tree, and then put alpha into f, then put t equals to uf, and lastly, increase I by 1 and go back, repeat 2. Okay, then finally the output will be a spanning tree, and we need to prove this. So let G be a graph and U a vertex of G. Then G is connected if and only if the graph constructed by the PF algorithm is a spanning tree of G. And moreover, if G is connected, the distance between U and Y in G equals dy for each vertex in V, and dy is also the same as the distance between U and Y in T. Okay, and so here are some remarks. First, we only need to prove the second half. So second half means the statement after moreover, because the first half is a consequence of the general algorithm for growing a spanning tree. So BF algorithm is a refined version of the general algorithm. So we must have this property. And the second remark is that so here we actually compare three distance. So first is the invariant dy, then second is the distance of uy in G, and then you have distance uy in T. Therefore, at the beginning, when we discuss the ambiguity of the defining of distance, so actually in this algorithm, these three are the same. So T is a subgraph, and you have bigger graph. So the distance in the subgraph is the same as the distance in the bigger graph. So there's no difference between these two metrics. In general, in metric space, you will have some situation like the distance in the smaller graph is larger than the distance in the bigger space. Okay, but here, due to the algorithm, we can conclude these three are same. Okay, next we are going to prove the second half. So we focus on the second half. So assume that G is connected, hence at the end T is a spanning tree. So in particular U is V. And then we are going to prove. We are going to show that first, dy is a distance between u and y in the tree T. Okay, so first, very trivially, we have du is 0, which is also the distance between u and itself in T, also in U, also in G. And suppose that exists y in V such that dy is L. Oh, sorry, here. Here we should aim at showing dy is the distance between u and y in the graph G, in the whole graph G. Okay, so here suppose we can find a point V such that dy is L, which is greater than the distance between u and y in G. So assume that, so let this to be K. So assume that K is the smallest number with this property. Then exists a path gamma starting with u, end up with y, and totally you have k plus 1 vertices, or have length, or equivalent have length, has length k. In G, joining u and y, and k is the length of gamma less than L, which is dy. And then the distance between u and xk minus 1 is at most k minus 1, and hence, because by the minimality of k, so minimality of k here, and hence dxk plus minus 1 is less than or equal to k minus. If this is greater than k minus 1, then k minus 1 is so is smaller than k, so k is not the smallest one. And then since y is adjacent to xk minus 1, it follows from the BF algorithm that we would put dy equals to k, or some smaller or certain smaller number. So why this is smaller? Because y could be already picked. Then this is a contradiction, because by our algorithm, dy is taken to be the smallest such number. Okay, so we are done. And so this is a contradiction, which means that we cannot assume that dy is greater than the distance between u and y in u and y in G. Okay. Okay, then let's look at certain examples. So example 1. So each BFS. Note that in the intermediate step, probably you might have multiple choice. Therefore, even for the BF algorithm, you might have a lot of spanning trees generated from that. So each BFS tree or complete graph Kn is a star. You have x1, x2, so here's x0, and xn minus 1. Okay, and then example 2, if we look at the hexagon, and then we can also write down the dy number. Here du is 0, dx is 1, 2, 3. But when you generate the trees, there might be several choices. So this is one possibility, and that this is the other possibility. Okay, and then if we look at hypercube, or when n equals 3, then you might have the following spanning trees. Actually, this is an important question to count how many spanning trees you can have according to certain algorithm. Okay, and we will come back to this algorithm at the end when we discuss a modified version, when you're taking care taking the weight on or the length of each edge into consideration. Next, we just introduce a depth first spanning tree algorithm. So we still make the tree rooted at a vertex U. So the idea is proceed in the forward direction as long as we are able. When it is no longer possible to advance, then we will backtrack to the first vertex from which we can go forward. So here actually we will make precise the meaning of first. So first means nearest vertex from where you're stuck. And it's a good idea to make certain comments here. Probably you don't have a concrete feeling of BFS and DFS, so I would like to make some remark. BFS, just like undergraduate study or undergraduate education, you need to have a certain liberal arts education, no matter what is your major, and you can declare various majors, as many as you want. Okay, but what is DFS? DFS is a PhD study or problem solving, doing research. You need to get into the problem deeper and deeper, and when you're stuck, you need to get the nearest way to do the detour. Okay. So, because for research or problem solving, there's little credit for even the second inventor. You need to be the first on something. Although the thing is very tiny, but you're still the first. There's no second on any huge part of it in science. No matter how relativity is, how great the general relativity is, people only know Einstein. So after Einstein, so even if you reinvent the general relativity, it makes no sense. So that's a difference. For DFS, you need to go the deepest way. Okay, now let's describe the actual algorithm to grow the FS tree rooted at U. So let G be a graph of order n, and U a vertex. So first put the counter to be 1. U, capital U, is vertex set consisting of the vertex U, and df number, dfu, is 1. So here df number is the one we care about, the invariant we care about. F is empty, T is the tree. This is the initial data. And secondly, if there is no edge in G that joins a vertex X in U to Y not in U, then stop. Later on we will show that when we stop, we have a spanning tree. Otherwise, determine an edge alpha with X in U and Y not in U such that X has the largest depth first number dfx, and do the following. Put dfy, increase dfy by 1, and put y into U. Put alpha into F, and put T UF. Then increase I by 1 and go back to 2. So here the crucial thing is when we choose X to be the largest step first, has the largest step first number. Recall that we stop at the place with df number I, and you need to find the largest one, that means which is closest to I. So that corresponds to the first here. This corresponds to the first. Okay, and if you look at the algorithm, it's pretty similar to the general algorithm or BF algorithm. The only difference is when we choose the new vertex, we use a different rule. Okay, and then we have the following theorem. G is connected. G is connected if and only if T is a spanning tree. OG. And we still look at the examples illustrated for BFS. So each DFS tree of the complete graph Kn is a path. And example 2, for the hexagon, we have a path. The DFS tree is a path. And for the hypercubes, DFS tree, a DFS tree is, you might have a lot of different trees. But here's one. So actually this will be either the Eulerian trio or the generating permutations. There will be a similar description for all the DFS trees. And another very interesting remark I'm going to make is if G is a tree, then BFS tree and DFS tree OG is G itself, Okay, so from the topology, there's no difference, but the important thing is, however, the order in which the vertices are visited are different. So this is important because in reality, this is how we search a graph or store and use and referring to the informations. So we, based on the BFS number and DFS number, we have the breadth first search OG or depth first search OG. So more explicitly, the tree G may represent a data structure for a computer file in which information is stored at places corresponding to the vertices OG, and to find a particular piece of information, we need to do search. We need to search each vertex of the tree until we find the desired information. And if you, I would like to give some picture to illustrate the difference. So for the BFS trees, it may look like this. Something similar to the fractals, self-similar fractals in mathematics. So this is BF. And then for DF, so you might like piano curves. Okay, goes deeper and deeper and then return from some place whenever you cannot go any further. Okay, so this is just an introduction to this BFS and DFS algorithm. And in reality, if you want to learn more, you better to check the applications in computer science. When you do some search problem on the code some small games, you might use their ideas. So from the application, you will know that better. For example, we haven't talked about the complexity of BFS and DFS algorithm for certain specific coding program, and we never talk about time consuming for that. So those are very very important in computer science. When you choose some algorithm, the most important thing is you need to choose the right one for your purpose. We do have a lot of algorithms, but not everyone is good for your purpose. Okay, next we introduce a little bit more complicated situation, that is net graph. Actually, we mentioned this before. So based on a graph, we assign a weight function. Then G omega is called network. Actually, in different textbooks, they might have different notion, and the notion I mentioned here is also different from our textbook, because in textbook they use a directed graph or weighted graph. Weighted graph is not a common terminology nowadays. And the thing he called the net graph, probably it's better to call the directed graph or whatever. So when you have this kind of problem, it's better to make precise the definition at first, so that all the people are in the same pace. And then it's easy to extend the weight function to any work. So recall that weight function is a function from the set of edges to real numbers to any work. Gamma as follows. It's just a summation. x0, x1, x1, x2, xk minus 1, xk. Definition. Weighted distance. So d omega, here omega denotes weight between a pair of vertices x and y of G is defined by minimal work gamma joining x and y. So from all works joining x and y, you take the minimum of the weight. And if no such work joining x and y, let dc d omega xy to be positive infinity. And here, actually, we need to have a remark, that is, d omega xy may equal to negative infinity according to our definition. Because if you look back at the definition, we never assume omega is a non-negative number. Then if you have this situation and you just repeat the loops again and again, then we have smaller and smaller length, smaller weight. Okay, then if we don't like infinity, negative infinity, or negative number appearing, we need to make certain assumptions on omega. So first, if we assume omega is non-negative, then there's no such question anymore. Or we can assume there is, because we have loop here, so there is no negative cycles. There are no negative cycles. And with a certain minor tiny assumption. Okay, and for simplicity, in the following, we will consider the case omega is non-negative, but you have the flexibility to allow omega to be slightly negative. This is also useful in our real problems. And remark 2 is if omega is strictly non-negative, then strictly positive, then d omega is d omega is distance in the following sense. So first, this definition for distance is true in any metric spaces. So first, d omega is non-negative, and when it's 0, if and only if x is y. And secondly, it's symmetric. And thirdly, we have the triangle inequality. This is quite useful when we study the metric spaces. Okay, next, recall that if we take omega, if omega is constantly 1, then it just the previous distance we studied for BFS method, breadth first trees. Okay, and then here we are going to find a certain tree which compute d omega xy, ux. And then construct a spanning tree T rooted at U such that the weight distance between U and Y, U and X in T equals d omega ux. This is the distance in G. Then we can call such tree distance tree. Before we proceed, I would like to make a remark. That is, here we only say that d omega ux is the distance between U and X in T. This is true, but we never see for any pair of points d omega xy is the distance between X and Y in T. This is too much. Okay, this is too much, cannot be true. So, okay, and then when omega is 1, when omega constantly 1, BFS gives a solution. And now this can be viewed as a generalization of BFS method. So this is called Dijkstra's algorithm, or algorithm for a distance tree for the weight omega. And now let's do setup. Let G VE omega be a network such that cardinality of V is N, U is a vertex of V, omega is non-negative. And then first, put the capital U, the set capital U, as a set consisting of small u, du is 0, f is empty, and t is uf. And secondly, if there is no edge in G that joins a vertex x in U to a vertex y in U, then stop. So you can output. Later on we will show that this must be a spanning tree satisfies certain properties. Otherwise, determine an edge alpha with one endpoint in U and the other endpoint in V, and most importantly, dx plus omega xy is smallest. And then do the following. First, put y into U, put alpha into F, put dy, set up dy equal to be dx plus omega xy, and go back to step 2. So here, the important thing is when you choose x and y, first you need to choose an edge with one vertex in, one vertex out, and then you need to choose such a pair where the weight is smallest. For a finite graph or locally finite graph, you can always do that. Okay, then theorem says if G is connected, if and only if T is a spanning tree, T is the graph, the tree generated by the algorithm. Dijkstra's algorithm is a spanning tree of G, and then moreover, if G is connected, then d omega uy is dy. This is also the, which is also the weighted distance between U and Y in the weighted tree T. The weight, so I should recall that the weighted distance in a tree is easy to compute because you only have a unique path connecting each pair of points in a tree. So you only need to sum them up. There's no process like taking minimal. Okay, so the proof, we will only we focus on the second half. The first half follows from the general algorithm for growing and spanning tree. And then assume G is connected, and hence T is a spanning tree OG. Since there is a unique path joining U and X in T, so dy by the definition is the distance between U and Y in the tree T. So next, we will show that d omega uy is dy. So trivially, du is 0. And suppose that there is a point y violate this, such that dy is strictly greater than the distance d omega uy. And we always push this to the extreme case. We assume that we can assume that y is the first vertex put in U with this property. Then there is a path gamma joining U and Y, and whose weight is omega gamma less than dy. And then let xj be the last vertex of gamma, which is put into U before Y. So here I should make a remark that such xj exists since first y is different from u. Okay, because du is 0, so it's always true. And secondly, u is put into capital U before y. Okay, so the set of all the vertex put before y is non-empty. You can talk about the largest one. Okay, this step is non-trivial. Okay, then by our choice, y dxj is d omega uxj. This is because y is first. So first vertex put into U satisfy this property. Okay, each sentence has some use for our proof. Okay, then consider gamma prime to xj plus 1 and gamma double prime to xj. Then we noted that then dy greater than strictly greater than d and greater than or equal to omega gamma prime, because y is after xj, so xj plus 1 is at most y. Okay, so gamma prime is smaller than the whole set gamma. And of course, here you use the property that omega is non-negative. Okay, then for omega gamma prime, it's omega gamma double prime plus omega xj plus 1. And this is dxj plus omega xj plus 1. Okay, then what's a problem? That is, hence, xj plus 1 is put into u before y, which contradicts our choice. Oh, xj. So it's a contradiction, and our assumption that exists such y is not true. So we showed that the resulting tree from the Dijkstrata algorithm is always a distance tree, compute distance from the rooted points. Okay, I will stop here. Next time we will talk about more on the network on the flow, with the flow.